Okay, corn children. This is going to be a quick little review of all things logarithmic. Well, not all things, but a lot of it. So this is primarily our chapter 3 material. Some of it I think shows up again in chapter 5. All right, so first of all, what the Haiti-ho is a logarithm? Here's our definition. Oh, by the way, if you need to, pause, rewind, do whatever you need to. Watch the video over and over again. I know I will. All right, so here's the idea. Definition of a logarithm. This is an exponential equation. This is a corresponding logarithmic equation. They are tied together if and only if two sides of the same coin. And here's your key thought. The base of the exponent becomes the base of the log. Notice that the exponent is now what the log is equal to. Logarithms give you access to, logarithms behave like, logarithms are essentially a former exponent. So from this, we actually get an interesting property. Comes in really handy. If you have the log base b of b raised to the x power, we're in essence invoking the fact that these are going to be inverses of one another. These will undo each other and you get just x. How do you know, Mrs. Klein? I'm glad you asked. If we rewrite this from a log equation to an exponential equation, check this out. This would become b raised to the exponent of x equals b to the x. Well, of course that's true. While it's perfectly clear that this is true, this is less obvious. So, idea. If you can make the base of the log and the base of the exponent the same, they undo each other, you just get x. Alrighty, that's going to come in handy, by the way, in the closure. We also have laws of logarithms. These are the idea of taking and rearranging, combining, pairing apart all kinds of logarithms. First property, it's my favorite, it's the power rule. If you have the log base b of a raised to p a power, you are allowed to take this exponent and move it down in front as the scalar. Just multiplying, just plain multiplication. Or if you want to, if it's helpful, you can take a coefficient and move it out of the way by making it the exponent. That is so handy. I know, right? Next property. If you have the log of a product, two things multiplied together, you can break these apart into little logs using addition. Or, because it's an equal sign, if you have two logs and you want to turn them into a single log, if it is addition, you can do that with multiplication. Interesting. We also have a division rule for logarithms. If you have the single log of a fraction, you can break this up into little baby logs with a minus sign. Now, I want you to notice that if we were traveling this way across the equal sign, we can go from two logs to a single logarithm. A single log. Two logs here, one log there. Two logs here, one log there. Why would we want that? Well, in our definition of logarithms at the top, we are talking about a single log expression. So if you have two logs and you want to turn it into a single log, you can do so using those properties. All right, so where does this come in? Let's do an example. We're going to put a lot of these together in one deal. Here we go. Let's suppose that we are asked to solve, yeah, that's right, solving, the following equation. 2 log base 4 of x minus log base 4 of x minus 1 equals 1. Now, how on earth are we supposed to do this? Well, first of all, I'd like to rewrite this as a single log expression. Not a two log expression, but a single log expression on the left-hand side. There's a small problem, though. When I try to use this law, which I will in a minute, there's no coefficients here. There's understood ones and there's a 2 here. So the first thing I'm going to do, I'm going to move that using the power rule in order to get this out of my way. So this is the log base 4 x squared minus log base 4 x minus 1 equals 1. Now I'm going to use this property, which turns it from 2 logs to 1 log. I do not write log. It is a single log, 1 log, x squared divided by x minus 1 equals 1. Interesting, I now have a single log equals a number. What do we do with this? We go all the way back to the definition. If you have a single log expression, you can rewrite it exponentially. I'm going to take this single log expression and rewrite it exponentially. 4 is the base. 1 becomes the exponent, and I set it equal to the expression x squared, x minus 1. If anybody's a fraction, I make everybody a fraction. I'm going to cross multiply, going quickly here. Again, if you need to slow it down, please feel free. Distribute the 4, distribute. Set it equal to 0. I do not like my quadratic term to be negative, so I'm going to bring, distribute, come on. I'm going to distribute, and then I'm going to set this equal to 0 by bringing the 2 terms across. Minus 4x plus 4. Bless your heart, some of you will struggle with this, but I am going to factor. The only things that multiply to make an x squared are a 1x and a 1x. Factors of 4, positive 4. They're 1, they're 4, they're 2, they're 2. These have to be the same sign, so either both positive or both negative. In order to get a negative 4, I'm going to work negative 2, negative 2. I set the factors equal to 0. No, I'm not going to write it twice. It's the same thing. And I solve. Now, just real quickly, we're going to check this solution because you cannot take the log of a negative number. So I'm taking my answer, x equals negative 2, and I'm going to check in here. Can I take the log of 2? Yep. Can I take the log of 2 minus 1? Yep. If you want to go through the whole thing, solve it all the way back through, that's fine, but this is our solution. Now I have demonstrated 2 of the properties and the definition all to get this done. I hope this helps you with Chapter 3's closure problems. Good luck, corn children.